Alright, so for homework 5, part A, the first part will be creating a log plot of the drag coefficient as a function of Reynolds and explain qualitatively the steep drop in drag coefficient at RE of around 300,000. So we're going to start by importing Alright, so for homework 5, part A, question 1, we're going to be creating a log plot of the drag coefficient as a function of Reynolds number and explain qualitatively the steep drop in the drag coefficient at 300,000 with the given efficient for spheres. So first we're going to import our normal things. So then we're going to do, again, import, Alright, and then we're going to do def of C, D, RE, and then we're going to list what's given to us in the problem, RE over 5, B equals RE over 2.63E, 5, C equals RE over 1E6, yeah, and then we're going to return our 24 over RE plus our 2.6 times A divided by 1 plus A to the 1.52 plus our 0.411 times B negative 9 divided by 1 plus B negative 9, and the last part 0.25 times C divided by 1 plus C. Alright, so that's our return, and then we're gonna do our x is equal to our np.log space of battery's low. Put this in real quick. Okay, there we go. Alright, the log space of, we do 1, oh, I already did that, 1, 7, 500, and then we're going to do our coefficient, or drag coefficient values is equal to C, D of X. Alright, and then we are going to fig is equal to make subplots, and then we're going to do fig dot add underscore scatter, and here we're going to add our x equals x and our y is equal to our cd underscore values. And then we're gonna decide that mode is equal to markers. And then we do fig dot update our axes for type is equal to log. And then same thing for the y value, or the y-axis. And then we're gonna do fig dot update layout, and that is gonna be our height. Well, we usually start with width. I think width is equal to 800, height is equal to 800, and then template is equal to plotly underscore dark. Oh, I think for this one we're supposed to use a line. Actually, that doesn't look right. Okay. And then for the explanation of why this is at such a steep decrease in the drag coefficient is because when air is moving around a sphere, there's a high pressure in front of the sphere, and then the air goes over, and there's a low pressure on the other side from the air going above and around on both sides, above and underneath. And when you get to a Reynolds number of 300,000, it creates a turbulent flow, and that actually helps to increase the like, not spins, but it increases the airflow around the ball to essentially decrease, or it increases the pressure on the low pressure side, so it drops our drag coefficient. It essentially just helps decrease the drag coefficient. And then moving on to calculate and plot part 2, the trajectory of a ball launched at 70 miles an hour and at an angle of 30 degrees to the horizontal until its first bounce, using the above correlation to account for the drag force. Assuming ground is horizontal, how far does the soccer ball travel before its first bounce? So for this problem, we're going to start with our variables like we normally do. I'm going to go through and list all of these out and then fill them back in. D, M, mass, area, position of X initial, position in the Y initial, and then we're going to have initial velocity, and then we're going to have our angle, which I'm going to call theta naught, and then we're going to have velocity X theta, velocity Y theta. Alright, so like I said, gravity is 9.81, our rho of the air is 1.2, our mu of the air is going to be the 1.8 e to the negative 5, our diameter of the average soccer ball is 0.22 meters, and then the mass of that is going to be 0.31, and then our area is np dot pi times our diameter squared divided by 4 because it's a circle, and then our initial position is 0, so is our, or for X and Y, and then our initial velocity was given as 70 miles per hour, but we have to convert that, and the conversion to that is 0.447, I believe. And then our theta is going to be 30 times the 30 degree angle times the NP NP of pi divided by 180 to convert to radians, and then to figure out our X and Y velocities from that, we're gonna do some simple trig, and it'll be v naught times our np dot cosine of theta for our x, and then similar for our y, v naught times np dot sine of our t theta. And we should be good on that front. So then we're going to do the def RHS of our t vec. And then we're going to say what our vectors are. So vx, vy, px, py are equal to our vector. Oh. Okay. And then from here, we're going to say what our v is, and that's going to be the square root of our vx squared plus our vy squared. And then we can do our Reynolds number, which is same as usual, rho v d over mu. And then we have to say what our force is, and that's going to be our drag coefficient with respect to our Reynolds number, times our area times rho times our v squared divided by 2. And then we can return our, I have these written off to the side. So we have our negative f over our m times vx, but we also, vx divided by v, and then we also have the negative g, negative f over our vy over v, and then we just have our vx and our vy. All right, so that's good for that one. And then we're also going to want to define the when the ball hits the ground, and I've decided that's just going to be ground t vec colon, and then we're going to return vec for 3. Oh, I spelled return wrong. Jeez. Okay. And then we go back and say ground dot terminal is equal to true, and then ground dot direction is going to be equal to -1. And then we do 10 is equal to 10, and our result is going to be equal to the solve IV function for our RHS. And then we have to do our 0 to 10 here, and then we also want to include the vector things, our Vy, our Vx naught, Vy naught, and then we also want the Px naught and our Py naught. And then here we're gonna include events equals ground, and then we include our dense output is equal to true, and then let me review this real quick. 0, I don't think I got any typos right now. And then we can do result dot t of events for 0, and we get 3. And then our t-plot is where we're gonna do our p dot linspace In this, we're going to want to include the 0 and then our result.t of events. Here, and then, what's going on? Oh, weird. Okay. Nope. And then we're going to want to do a v-plot, the x-plot, the y-plot, and then we also want a position x-plot, position y-plot, and these are going to be equal to our result.sol for t-plot. And then, because this is a second figure on this, so we say fig 2 is equal to, make subplots, parentheses, and then fig 2, we're going to want to add I'm getting my things backwards. Fig 2 dot add underscore scatter. We want our x to equal our x plot. Sorry, our p x plot. Our y is equal to our p y plot. And then our mode this time is going to be markers. And then we can update our layout like we normally do. Nope. Update layout. And that's going to be with our width being equal to 800, height equals 800, and our template is equal to plotly underscore dark. And let's see what we get here. Alright, so it looks like it lands just past 60 meters. That's what this is, even though our axes are not labeled with correct units, or any units really. So that is going to be our answer for how far it lands. And that is all for this part of the homework.